Hello, everyone. Welcome to our third speaker event of the seminar series and distinguished seminars in optimization and data, which is a new series that we started this year, earlier this year in January. It is actually a joint effort that came together by faculty from different departments, the ECE, CSE, Math, Statistics, and Applied Math departments, as well as the IFDS, Institute for Foundations of Data Science, that's a supporter of this seminar, and PIMS, Pacific Institute of Mathematical Sciences. So we acknowledge all these sponsors for the seminar series. And the goal is to bring speakers to campus that can reach out to a broad range of people in different departments and work on really interesting stuff that appeals to multiple people, multiple groups, and has different perspectives. And a really good example of that is our speaker today, Professor Misha Belkin from UC San Diego, Computer Science Department, as well as the Halicioğlu Data Science Institute in San Diego. He has done really great work. So he's a professor there at UC San Diego. And prior to that, he was a professor at Ohio State University. He's done really important work in trying to explain how machine learning systems work. And in particular, one line of work that he really started and did seminal work in was to explain how overparameterization works in deep networks, and a lot of other excellent work that has followed. So we're very excited to have Misha here. And without further ado, I'll pass it on to him.
Thank you very much. Thank you for a kind introduction. And yeah, it's really great to be here. Yeah, so I would like to talk about today is essentially the way of thinking about really large neural networks, and in particular, like, why cannot we train infinitely large neural networks? And what's, I'll justify this idea of training large neural networks shortly. But that's the kind of premise of this talk. And by the way, please feel free to interrupt me and ask questions. I'm more than happy to, slow down and discuss anything. In particular, there is, I think, quite a bit of material here. If I don't go over all of it, it's OK. So this is joint work with collaborators, with Daniel Beagle-Hall, my student at UCSD, Adit Radhakrishnan from MIT, Amir Hissan Abed Sultan, also from UCSD, Parthy Pandit, UCSD, and Siyuan Ma, who was my former student, who is now at Google. So, well, let's start. So first, we all know that the size of neural network has been growing rapidly in recent years. And this is 2017. The circles, each circle represents a neural network architecture. Big circles are about 100, 200 million of parameters. Small circles are about 6 million of parameters, right? This seems puny by modern standard. This is GPT-3. This is to scale. Now some models are even bigger, on the order of trillion parameters. So, like this is a nice summary of some recent language models. Basically, I think it's about 100 billion and trillion parameters and trained on a similar amount of data, roughly the same number of tokens, plus or minus, between 100 billion and a trillion. And maybe GPT-4 is even bigger, we don't know. So more parameters, more data. And what is less known is the number of authors also scales with the number of parameters.
With the log?
I don't know. Good question. Maybe linearly. OK. So here is an interesting quote from, so in this paper, OpenAI. They analyzed scaling laws for neural language models. This was about 2 years ago, I think 2021 maybe. I think there is an interesting a series of interesting observations. And in particular, they say that performance depends most strongly on scale. And the scale consists of 3 factors: the number of model parameters, the size of the data set, and the amount of compute. And obviously, the amount of compute is closely related to the other 2 things. They actually say that the performance depends weakly on other architectural hyperparameters. OK? So now if this is true, right? Why not take the number of parameters to be just infinite, right? If that's one of the main issues. And you can say, okay, well, this is obviously not possible. This is a rhetorical question, but it's not rhetorical. Why not? Well, because we already know that such things exist. In fact, we had like this whole history of using theory of reproducing kernel Hilbert spaces with mathematical object. And it goes back to, splines in the 70s and 80s and kernel support vector machines and kernel methods more generally, in the 90s and 2000. And very recently, last 5 years or so, we have found out that very wide neural networks, at least in some regimes, are actually mathematically equivalent to these kernel machines. So building infinitely wide neural network explicitly is quite possible. Now, let me very briefly remind you what these kernel machines are and how they actually work. The idea is very simple. Well, so mathematically, this corresponds to some sort of, and I'm taking and interpolating kernel machines. You can add regularization if you want. This is just a simpler formulation. So this machine will fit the data exactly the way I wrote it. But basically, you want to fit the data over some class of functions, and you're choosing the form of the function which minimizes the norm. So you have some norm space with a norm. You're minimizing the norm among all functions which fit the data. For example, linear regression is a special case of this. Unregularized, I should say. Now, the nice thing is that this, in general, when you write it like this, of course, there is no, it's a mathematical formulation. There is no obvious way to compute this, right? How do you put this in a way that makes it an algorithm? And it turns out that for certain classes of spaces, those reproducing kernel Hilbert spaces, there is actually an explicit solution which is easily computable. So you have this kernel function, which is a function of two variables. Here it's xi and x. And your predictor has the following form. It's simply a sum of alpha with some coefficients. Alpha is real numbers, k of xix. So if you think of this, for example, being Laplace kernel just being this function, you can also think about Gaussian. If you put a square here, it's a Gaussian. So it's just a sum of this over all data points with coefficients. So it's in particular, if it's a Gaussian, it's a mixture of Gaussians, or with potentially negative coefficients. Now, how do I find alpha? Alpha is very easy. You just simply invert the matrix of the kernel matrix. What is the kernel matrix? Kij equals kxij. So this is a matrix whose size is n squared when n is the number of data points. So everything here is completely explicit. You just put it and you compute it. Now, there are challenges associated to this, in particular to the matrix inversion. I'll discuss this later. But assuming that we can do all these matrix operations, it's pretty good, right? Everything is closed form. Now, very recently, it's been shown that at least in some regimes, training a neural network is actually exactly equivalent to solving a kernel machine. And so this is exact. I mean, this is not an approximation. This is exact in the limit of the neural networks. It's not true for all regimes, and I'll discuss this later. Now, what is the kernel associated now to the network? It's actually, again, a fairly simple thing. So if you have an arbitrary, so this works for any neural network, but to actually have this equivalence, you need to have infinitely wide neural networks. So if you have a neural network, so fw, w is the vector of parameters, then to construct the kernel corresponding to this neural network, you take the gradient of your function with respect to w, and you take in the product of that with a gradient with respect to w. This one is at x, this one is z, right? This is a function of two inputs, and this is a kernel function, positive, semi-definite, and that's basically what it is. Okay? So notice this is defined for any neural network, but in general, this thing is not constant when you change w, right? So it can change during the optimization process. in which case it's not equivalent to a kernel machine, at least not the standard kernel machine that, with a fixed kernel. But if it's infinitely wide, then it is. So we have this direct transition to infinitely wide neural networks, which is somehow free in a sense, because we can compute this analytically for many neural networks. Okay, well, problem solved. Yeah, we're done. Well, not quite. Okay, let me now bring, the premise of the talk is that there are challenges, right? So what are some of those challenges? Challenge one is that there is generalization performance of a kernel is not always that good. And this is something that is referred to feature learning, and I'll describe. This is our recent work on the subject, so I'll show how we can deal with this challenge. That's challenge one. Challenge two is that how do you scale this to large data? And as I showed, you need to have like trillions of data points. We're not quite at the level of that, but there is, I think, a clear path now to scaling to much larger data, to at least billions of data points, if not trillions. Actually, yes, just scaling the number of data points is not that difficult. We can probably scale to trillions. The model is a little trickier. Okay. Now let's discuss feature learning. Well, first, actually, this is a result from our recent work with Adit Radhakrishnan, Stefanakis, and Caroline Euler from MIT. First, you actually can, even without any feature learning, you can do very well on certain problems just by taking this infinitely large neural network. And this is in particular for certain matrix completion tasks. So you don't even need, in some cases, about feature learning. But this is certainly the case that at least for some data set, if you just use a kernel, it's not as good. And let me give you an example. So this is what's called, the data set is called SVHN. And the goal here, it's house numbers, I think. And the goal is here to identify the middle digit. So here it's 3, 6, and 1 there. OK? And I can simply run Laplace kernel of this. I get 74% accuracy. If I run NTK, I get 79% accuracy. If I write the deep network, so this is NTK for the same network. So this is kernel corresponding to the network in the same way that I described before. You see that it's 5% better. So neural network is doing 5% better than the corresponding kernel. Yeah?
Does it mean that a finite neural network is doing better than an infinite neural network? That's kind of weird.
It might, yes. So in this case, it depends. So it's certainly true for this case. It depends on how you initialize it and what limit you take. But yes, if you just take the limit in the limit that I had before, then the finite neural network will do better than the infinite neural network. Yeah?
So that's a one-layer network, completely connected. One hidden layer network.
That's more than one. That's maybe 3 layer. I don't remember.
So it's not quite equivalent, or it is?
No. These two things, like the NTK is at 0 of this network, so they're completely equivalent. Laplace, of course, is different. But Laplace is like significantly worse than this. So yeah, so this is kind of kernel without evolution, and this is kernel with evolution, if you want to think about it that way. And clearly it's doing something because it's 5% better, right? It's a non-trivial improvement. Okay, so something is going on. And what is going on? Well, the kernel changing along the optimization path, that of course is very similar, very like, easy thing to say. But why is change good, right? So actually in the literature, very often feature learning is associated with the kernel being just non-constant. But it's not true, of course, that change is always good, right? Sometimes it's good, sometimes it's not good. It depends. So here is a very interesting result, very thought-provoking result from Phil Long, who is at Google. And he had a paper with, he showed empirically that if you take the kernel after training, what he called after kernel. So take a neural network, train the network, extract the kernel after training, And that kernel actually turns out to be as good as the neural network itself, and better than the kernel in the beginning. So this is saying that, okay, kernel does change in a way which is helpful, right? It matches a neural network. Not terribly practically useful, because if you have to train the neural network to get the kernel, okay, well, why bother, right? Like, who cares? Now, there is another line of research, for example, Damian Lee and Mahdi Sultan Al-Khattabi. And they, in certain cases, you can show that if it's a multi-index model, then you can recover you can recover the underlying model with gradient descent. I won't talk about this, but that's kind of another way to think about what feature learning might be. Yeah.
Remind me what a multi-index model is.
So like, let me just tell you what single index model is. Single index model, if your model just depends on one direction in the feature space, so your model is of the form you project onto this direction and take some nonlinear function. So multi-index is just the same for several. We will actually see an example of this very shortly. In fact, here, this is a two-index model. So, okay, let's do a really simple example to sort of understand what we're talking about here. First, so you have this data x in R100, right? So it's sampled from a normal distribution in 100-dimensional space. So that's nice. Now, the target function is deterministic. There is no noise here. It's just x1 times x2, right? So it doesn't depend on 98 directions. And now you realize very quickly that if you use a kernel, which is NTK of this network, your test R squared is 0.1. And for those who don't remember what R squared is, it's essentially the same as square loss, but it's normalized. So 1 is really good and 0 is bad, okay? So basically, 0.993 is very good and 0.1 is pretty bad. Okay, so basically, deep network works very well, and kernel doesn't work almost at all. Okay? So what happened here? Like, this is a super simple example, right? What can be simpler is just a function of the variables. This is the index model, two-index model. And kernel fails. So let me now kind of take a step back and let me define something. And so if you have a neural network, just take W1. Okay, this is a matrix for fully connected. Actually, it's defined for any neural network architecture. And let's call W1 transpose W1 the neural feature matrix, okay? Now, this matrix, the size of the matrix is the size of the input. It's D by D. Okay. Now, here is an interesting thing. So let's go back to the thing, and let's look at what the matrix of this network is. And you realize that the matrix is D by D, so it's 100 by 100. So you see that the first two coefficients of this matrix are actually quite large, the first diagonal two corresponding to x1 and x2. And the rest of them are much smaller. They're close to 0. So somehow that matrix learned that these two coordinates are important and the rest of them are not important. Okay, I'll describe what it means to learn more specifically, but I think this is something to think about as a specific thing. Now, here is the amazing thing. If I know this, if I know only that the first two coordinates are important and the rest can be ignored, I can actually run the kernel, and just with 20 examples, I get perfect R squared. So if somehow I can learn these features, then kernel does perfectly well. So that's, in a sense, what kernel is missing, right? It knowing something about that, and somehow a neural network finds it. OK, now here is a sort of a key insight, is that let's look at what this means. So let's look at the gradient of my function with respect to the input. Okay, this is not gradient with respect to the weight. This is gradient with respect to the input. The gradient with respect to the input at x1, x2, right, is just going to be x2, x1. And if you just average this thing over all of my data points, actually, in this case, you can just take average over the normal distribution. You see it's like 1, 1, and then zeros on the diagonal. So this average or expected average, I'll use this interchangeably, average and expected, gradient outer product matrix, which is just this times that transpose, gradient times gradient transpose, is the same matrix as what the neural network learned. Okay? And the expected gradient outer product actually like just select these first two features. And this is related, so this notion of EGOP is not new. It goes back at least 20 years. And in particular, Hristachi, Juditsky, Polzel, and Spokojny had a paper about like this type of object, like how to identify important features in 2001. And later work was also done with Samarik, Patufi, and other people. So what's going on? Like why EGOP? Why is this an important notion? And well, now let us think what it measures, right? So suppose now I change my input a little bit. And what do I want to see? I want to see how my output changes. Which directions of the input are important? If the direction is important, this direction better affect the output, right? If my direction of the input doesn't affect, if the change in this direction doesn't affect the output, then this is not important, right? So if you think about this kind of measure of importance, that's what it is. Now, what does EGOP measure? That measures exactly this. So largest eigenvectors, the eigenvectors of EGOP matrix with the largest eigenvalues is essentially measure that, while the ones with the smallest eigenvectors are features which are not important, I can ignore. So if you want to have some sort of optimal dimensionality reduction, you have to essentially project onto the span of the top eigenvectors of this EGOP matrix. Yeah.
This isn't going to be very useful in areas like vision and NLP, where all the input features have approximately the same importance, no? We won't quite get to this, but I have some, maybe at the end of the talk, I'm happy to give some comments about this. It's, so for vision, for example, you have to pass it through some convolutional features first. Because, yeah, if you just look at the pixel values, they're not going to. If your images are not registered, so if your images are centered and registered, it's fine. It will work just like that. But if, I'll show some examples. But if they are not, then you have to have some sort of filter pass. Yeah, but that's a good point. Okay, so now this is kind of maybe the key point here, is what we call the deep neural feature ansatz. And ansatz, by the way, if you're not familiar with this word, ansatz is like an assumption, but you don't really like, it's a simplifying principle. It's not really, this is not really true, that this is not really equal to this, but it's close to being true. It's something which we can usefully think of as a simplification. I'll explain in what way it's close to being true. So you can kind of think of it as being conceptually true, even though it's not a mathematical identity. Okay, so in any case, let me explain what it is. So we have this network, and we have W1, W2, and so on. At each layer, we have a matrix of weights. And now the claim is that this matrix of weights, so W transpose W, this feature matrix, we can just think about the first layer. So for the first layer, it's just W1 transpose W, and it will be simply gradient of the full model with respect to the input. If you wanted to do it for the next layer, you take W2, and instead of the input to the model, you consider the input to that layer. So it's kind of, could think of it as being recursive somehow. So that's basically what it is. It's essentially that identity. So the claim is that this is really the essence of learning features in neural networks. So that's some sort of definition of what it means to learn features. And let me give you some evidence showing that this is really accurate. So this is one example. So on the x-axis here, there are different data sets. This is a layer, and this is correlation between expected gradient outer products and this NFM, which is this matrix for the corresponding layer. And you can see that all of the correlation, well, the smallest is 0.59, which is still pretty good, but most of them actually are much higher, like 0.9. So yeah, these matrices are not exactly the same, but they're very strongly correlated. So they're essentially the same. And so this is maybe some graphical sort of representation of this. These are images of faces with, this is Celeb A, basically a bunch of celebrity faces. And there are these different tasks like identify necktie or smiling or rosy cheeks. The kind of binary problems. So this is a vector, feature matrix of the first layer. And we take the top eigenvector of it. And we can kind of take the top eigenvector to think that this is an image itself, because the matrix is it's not the size of the image, it's the size of the image squared. So the eigenvector of it is actually the size of the image, and you can think of it as an image. So if you're familiar with eigenfaces, it's exactly the same idea. And this is the expected gradient outer product, also top eigenvector of the same thing. And you can see that, well, they're not exactly the same, but they look very, very similar. So visually, at least, they're almost indistinguishable.
Does the correlation increases if you increase the width? Or
it depends how you initialize it. So here, initialization is very important. So if you initialize it large enough, then you're in the kernel regime, and then you wouldn't actually get this.
The non-NTK translation.
You need small initialization to have this. Otherwise, yeah, actually, I'll have an example of this. Okay, this is a pretty extensive, actually, evaluation of this 121 tabular data set from this UCI data. Yeah.
But why don't the nonlinears in the later layers muck up descent sets?
I think, that's why it's an ansatz, because it's not exact, but they somehow like average out. Okay, I'll show you some theory, but I prefer to show the practice rather than theory, because I think the theory is ultimately not that convincing, but the practice is actually much more convincing, at least in this case. I'll show some theory, though. We can prove something, but what we can prove and what seems to be true is there is a gap. But in any case, so this is correlation between initial NFM and train the feature matrix for each layer, for each one of this 121 data set. This is some sort of average. Well, this is a full distribution. And you can see that the correlation is very weak, but the correlation between this average gradient outer product and trained NFM is like 0.9 on average, actually above. In fact, it's like for the fifth layer, it's almost 1. So it's very strong. I think the effect is very strong. So let me maybe show how this actually happens in training a specific neural net. So this is detecting if celebrity images contain glasses. Okay, so she doesn't have glasses. He does. So there are two neural networks here. One is just fixed. So it's what they call NNGP. Basically, you just fix the structure and you don't change the layers. You just train the last layer of a neural net. That's non-feature learning one. You can do the same in the NTK regime. And this is the red one. And you can see, of course, the feature matrix is just random. Now, the feature learning one, you can see that it starts with something which is random, of course, because that's initialization. But after some number of epochs, on the x-axis, so the x-axis, you have the number of epochs, you see that this image of the glasses appears. This is a diagonal of the feature matrix. In this image of the glasses, actually, after about 10 epochs, it's pretty nice. Notice that the image of the glasses appear before the test error actually drops fully. So you already have pretty good feature selection here, but your predictor is not yet trained. Like it's only get trained about here 20 epochs, but that happens earlier in 10 epochs. So there is a mismatch between feature learning and actually predictor learning. But notice that you get, with the non-feature learning one, you get about 20% error rate, and with the feature learning one, you get 10%. So it's a big difference in accuracy. Yeah. What's that?
What happens at the plateaus? Where it
Here?
stops moving? Yeah, like it's kind of like a step.
So here, I think almost. Oh, why did it drop? I'm not sure actually why it dropped.
I mean, like going from like the from
Here.
where you have 20 test error, there is nothing happens, and then there is a sharp drop.
Oh, why does it a sharp drop like that? I'm not sure. It's that's a good question. I'm not sure. I'm not sure why it. Like you mean this point?
No, along the green curves, right? It kind of progresses very sharply.
That may be because there is some schedule for the learning rate. Actually, I'm not 100% sure why
This
it's
is a
dropping.
common behavior though.
It is a common behavior. Yeah. I think it relates to the learning rates, but I'm not exactly.
It's not fundamental to the learning process.
No, it's not. It's you see a lot of this weird behaviors. Yeah, I think what's more interesting here is that, like, after maybe about here, right, this already fully learned, so nothing really happens. But this thing continues going down for a while because somehow this doesn't have the benefit of having right features, so it somehow needs more training, it seems. Yeah?
I'm wondering if you talk about the picture at the very end of the green curve.
This one?
Yeah.
It's a little hard to see, but it's glasses. It's just slightly different. Like, it somehow emphasizes the nose more. It's still glasses. It's similar to this one, but it's like a little more concentrated on the nose. Okay. So now theory, okay. Basically, we can prove it under some pretty special conditions, which, so the width needs to go to infinity, the weights have to be resampled in some way or some, there are basically a bunch of like special setups which are required to prove it exactly. And it's kind of annoying, but yeah, definitely, at least in some cases, we can show that it's really like a mathematical theorem. Okay, but let me maybe continue because I think this is really important. Because now the question is, of course, okay, so suppose I convinced you now that this is what's happening in neural network. And if you think this is what's happening, then the question is, why cannot we just learn the features directly? Why have backpropagation at all? And the answer is, there is really no reason to have backpropagation. We can do it directly. And this is this idea of recursive feature machine. And let me actually give you an algorithm. It's rather specific. I'm going to use Laplace kernel, but you can use, actually this works with pretty much any predictor, but I'll use Laplace kernel to be specific. And in fact, it does work well with Laplace kernel. So remember the kernel machine? So I have this kernel, which is just e to the minus norm x minus z. And then I'm solving kernel regression, and this is just a short way to write kernel regression. It's the same formula as I had before. I'm inverting this kernel matrix. Now, okay, so I did this. I invert the kernel matrix, and I get something. And that something that I got was no good, right? Remember the example? Like, it's pretty bad. So what do? I say, okay, well, maybe it's not that good, but can I get something useful out of it? And what useful thing can I get out of it? Well, I can think that, okay, maybe the predictor is not that good, but maybe my feature matrix that I get from this EGOP, maybe that has some information. Now what I can do, I can actually compute, so this is my predictor, and now I'm computing this, and the beautiful thing about it, it's fully analytic, so it's just a formula. This is, in fact, exactly the formula. So I just do this. This gives me a matrix. And now what I'm going to do, I'm going to take this m, and I'm going to plug it in right back here. But instead of, so I start with m equals I. So instead of I, I'm going just to plug this matrix that I learned from this. Okay? So I updated my matrix. What do I mean by this? This is so-called Mahalanobis distance. So x, so I just need to define the normal. Oh, there is no board here. But x, so normal norm squared, right? If what's norm of x? Norm of x is x transpose x, right? That's norm x squared. Now, you can say that instead of X transpose X, you can put X transpose IX, when I is identity matrix. That doesn't change anything. Now, if I want to put M there, instead of I, I'm putting M. So norm X squared with index M is just X transpose MX. So that's, and so solve kernel machine, starting with I, find a predictor, use a predictor to extract features, and plug the feature matrix back and recompute your kernel machine. So do this a bunch of iterations. Actually, in practice, it's like 3 or something. It really doesn't require a lot. And it turns out that once you do this, like after one iteration, you already match the neural network. So it's very straightforward, actually, to get to the neural network performance. Yeah, so here, yeah.
Why do you call this recursive? Because it's iterative?
Iterative, yeah. Recursive sound. It's like a more better sounding word for iterative. IFM, I don't know. It doesn't. Okay. So actually, if you think about expectation maximization, there are these 2 steps. So it kind of has the same feel as some form of expectation maximization. Okay, so now you can actually do this RFM, and you basically, well, get slightly better result in neural, essentially the same. So you match neural network. And for that example, for the STO example with neural, this 100 Gaussians, also you get the same result. It's actually, so here is the claim. The claim is actually whenever you get better performance out of fully connected neural network than out of NTK, you can do this, and you will match a bit the neural net. So so we did it on 121 data sets, and it's actually it is the state of the art, I think, now on these data sets. So I think on tabular data, this is really the state of the art now. And the nice thing, actually, it takes like 40 minutes for this 121 data sets, and neural networks take 5 hours to train. They're pretty small, so it doesn't take that long.
So this is your repository?
This is a full repository, right? And there was actually this paper by Fernandez Delgado, so they compared 179 methods, and this is the best. No, this one, some of them, I think that was one of the parameters. Some of them we used Laplace, and some of them we used NTK for that neural network, which was used here. Yeah, I think that was one of the parameters. So we basically try do some grid search over parameters. All methods were trained the same way. Neural network also, but neural network had many more parameters to train. There are a couple of other things you can, like regularization amount is also a parameter. In some cases, regularization made some difference. No, not always. Okay, so now, I guess I won't have, yeah.
Sorry, I'm trying to understand why your recursive method will be better. Is it because you're actually learning a new magic by using the M for the data, and then you are trying to understand the underlying structure, the manifold structure of the data better compared to just use the standard magic in the Euclidean space?
Well, saying it's a manifold, giving it a little too much credit, right? It's just a linear thing. It's a manifold, but it's a very simple manifold, right? So basically, I mean, maybe that's way to think about it. Like in this case, you have only 2 coordinates, which are important. If you know those 2 coordinates, your kernel method is unbeatable. It's really, really good. The problem is, if you take a radially invariant kernel, it's going to get confused by this 98 coordinates, which are noise, and it's not going to do very well. But even that kernel, if you train it, it will give you some performance. And that performance is enough to know that these first 2 coordinates are more important than the rest. And once you plug this back in, your kernel improves, and then it gives you even better results. So after like a couple of iterations of this, you're basically doing very well. Now, why is it better than neural network? Well, in this case, it's actually not better. It's about the same. But why is it, like in those examples, better than neural networks? Because neural networks is learning predictor and the features at the same time. So it's very tricky to choose parameters. So you have two processes, and they're happening potentially at different pace. So for example, you can learn predict and you can feed data before you learn features. And then you're not doing so well. So I think for neural network, maybe in principle it can learn features always, but like it's really sensitive to things like learning rates and batch sizes and all sorts of like this. Which exactly optimizer you use, like Adam or Adagrad or whatnot. So in this case, everything is very direct. So I think it's just a much more direct way of getting at the structure. Okay, so maybe let me just make a couple of points here. So once you sort of think about this way, that is, this is EGOP, a lot of things which are kind of strange make a lot of sense. And maybe, just in the interest of time, maybe I'll discuss lottery ticket hypothesis. Because how does it make sense? First, what is this lottery ticket hypothesis? That was Frankel and Carbon, I think, like 4 years ago, I guess. They found the following. So you take a neural network, you train it, and then you threshold the weights just to leave the biggest weight. Like you leave like some, I don't know, 5% of the biggest weight. And the rest of them you set to 0. Now you have this sparse neural networks, and then you retrain the sparse neural networks with the thresholded weight set to 0. So all the weight which was 0 just set to 0. So you train this sparse neural network, and it works as well or better than the original one. Okay? They call it the lottery ticket hypothesis because it's like winning the lottery, finding some network which works better.
What was the architecture of the networks that you used in the experiments?
These were all fully connected.
And how many layers? One layer?
Between 1 and like something 6 or something. Yeah. Something like that, yeah. Yeah, so why does it make sense from this point of view? Well, actually, so let's think about Glass's classification. So this is the diagonal of this RFM feature matrix. So if you run an RFM, you look at the feature matrix that it learned as M, you actually see this. This is the same pattern as we saw before. And if you just threshold it, you have like 1.5% of the pixel. And just threshold at 1.5%. Oh, why is there so many of this? And basically what happens is with glasses, you have like 1.5% of the pixel, and you actually get higher accuracy than before when you train on this. This is equivalent to pruning the first layer of the neural network, right? Because you are removing all weight which connect from these other pixels which have been removed to anything in the higher layers. So it makes perfect sense, right? Why? Because you really don't want to train on these extra pixels. They can only confuse you because you know that all the information is contained in this area. That's all you need to predict glasses, right? If you're predicting glasses and you're looking at the mouth, that can only confuse you. That cannot help. So this is very, very consistent for like a bunch of these tasks. For a lot of them, you can remove like a few % of the data and you actually get better. A few % of the, you can only keep a few % of the pixels and you get better accuracy. Yeah?
Different images will have different locations for the glasses, right? Like in some image, the glasses could be in the top left corner.
Correct. So that's not in this image. So that's why I said these images need to be registered if you want to use fully connected. With convolutional, you can do other stuff, but then you have to look at, we're actually currently looking at that. There is something similar happened there too, but you cannot look at it at the pixel level because it's not translation invariant. This is not translation invariant, right? It's assumed that the faces are registered. Now, if you're familiar with the statistics, you may have heard about debiasing, which is actually a very similar idea in statistics. What you do with debiasing, if you do, say, linear regression, you choose a few coefficients which are large, like, say, you fit a linear model, then you choose coefficients which are large, and then you set all other coefficients to 0, and then you retrain only on those coordinates which have large coefficients. If you think about it, this is like a nonlinear version of debiasing. And that's basically, I think, directly what lottery tickets are. Now, okay, there is I don't really have time. Grokking is actually another one of these very interesting things. There was a paper from Google about what they call grokking a few years ago that also can be explained from this point of view, but I'll skip this. Okay, so in any case, there are like a couple of things, like several of phenomena of deep learning, which sort of perfectly make sense from this point of view. And yeah, I'm happy to take it offline. But let me, in the remaining few minutes, I would like to say something about scaling, because that's a complementary challenge of this. So now, okay, well, suppose we know how to do feature learning. This still doesn't solve the problem, even if we can beat neural networks, because these neural networks scale to huge amounts of data, right? Trillions. What do we do with kernels? And the problem here is that if you look at standard kernel methods, if you just do it very naively by matrix inversion, right, you have n times n matrix, n number of data points, and this operation can take n cube. Okay, in practice, it doesn't really take n cube, but you can imagine n cube is bad, right? In practice, you cannot really solve a system if it has much more than 100,000 data points, maybe 200,000, because there are a number of issues. You basically cannot even store that matrix. Now, let me very briefly describe this idea of preconditioning eigenpro, which is joint work with Yuan Ma, and from a few years ago. And then I'll say something about the new, what is missing there. So basically, the idea of eigenpro is the following. You have an original kernel, and you want to precondition it. And how do you want to precondition it? Basically, what is bad for you is to having spectrum which decays quickly. And you want the spectrum to be as flat as possible. And this is, I'm going to solve it using gradient descent, actually stochastic gradient descent. So this is preconditioned stochastic gradient descent. You want to make the spectrum flat. I guess if you're not familiar with this type of ideas, you just have to believe me that flat spectrum is better. Now, how do you change the spectrum? Well, you can find the top few eigenvectors and literally just rescale them. And that's basically the idea. You're essentially constructing a new kernel, which has the same spectrum as the old kernel for small eigenvalues, but has a flat spectrum for the first, say, 100 eigenvalues. Now, this is not super practical, what I just said. But how do you make it practical? The practical thing, you're constructing the following preconditioner. And this precondition is simply I minus the sum of 1 minus lambda k plus 1 over lambda I, EI transpose, where EI is the ith eigenvector of the kernel matrix. And then the precondition stochastic gradient descent is simply this formula. It's super simple once you have this. Now, okay, if you, as they say in the literature, an astute reader will notice that this is not practical either. Why? Because I have to compute eigenvectors of this big matrix, and computing eigenvectors of a big matrix is not much easier than actually solving a system of that size. What do I do? Turns out, here is the cool thing. For top eigenvectors, you don't actually have to compute the eigenvector from the full matrix. It's enough to take a subsample, and after that, you can do an Nystrom extension. So if you're not familiar with Nystrom extension, it's basically a way to pretend that a small matrix is like a big matrix. Okay, so I can take, if I have 1,000,000 data points, I can take a submatrix of this 1,000,000 data points, and I can basically take these eigenvectors and extend them. And once you do this and plug in there, it all works very nicely. And you can basically scale up to about 1,000,000 or 2,000,000 data points. So now, unfortunately, it doesn't quite solve the problem because we want 1,000,000,000 data points. Well, 1,000,000,000, okay, at least maybe 100 million or something. So let me skip this. Here is a problem. The number of centers is n. And this is the same thing as the data size. And we need to actually decouple model size from the number of centers, from the number of data points. So for a kernel machine, the number of centers and the number of data points are, the model size and the number of data points are coupled. That's a problem. They have to be different. And actually, it's very easy to see on this. This is a really small example. This is a model size. And this is the data size, okay? So model size, okay, so you can see this is very consistent with these deep network things, except on a much smaller scale. Model size 2,000, 4,000, 8,000, okay, bigger model always is better, clear. Data is more is better. But look at this. If I take a small model size, like that one, then a small model size with 16,000 data points is about the same as a much bigger model size, or 4 times as big, with 8,000 data points. So it's much better for me to train a small model to get to this performance, right, than a big one, because that scales linearly with the number of data points. The big one scales some quadratically or cubically or something like that. So I really want to have some way to scale this independently, and that's one of the key tricks, I think, in machine learning and neural networks. And I don't really have time to talk about this, but there is what we call EigenPro 3.0, which is preconditioned projected stochastic gradient descent. So you have a number of centers, and you run stochastic gradient descent, and then once in a while you do a projection. Actually, the projection itself is a preconditioned stochastic gradient descent, but basically there is some sort of iterative way to solve this. And that works for much bigger models now. You can, you can train like 1 million of centers on 5 million data points. And this 5 million is not the limit you can scale. So we actually did some experiment with 100 million. So in terms of the data scaling, there is no limit to this. It's just a matter of computation. It scales linearly with the number of data points. And you can actually consistently see bigger models is always better. It's amazing. This is the same thing. Bigger model is better, more data is always better. It's same thing over and over again. Yeah, and it kind of, it's right now it is a state of the art for kernel machines for this type of data. Okay, I'm running out of time, so let me just make a couple of concluding thoughts here. First, I think kernel machines capture key property of very large neural networks and already state of the art on tabular data. Now the question is what happens with depth, and I have some thoughts, but maybe I'll take them offline. It looks like for fully connected neural networks, depth really is not that important. For convolutional ones, it seems that it might be important, but this remains, I think, to be seen. Now, scaling to at least 1 billion data points is now possible. It's just a matter of, getting the right resources for this. Now, concluding thoughts number 2. Recent efforts and, no joke, immense resources. So I think the resources have exactly the same, well, roughly the same number of zeros as the number of training points. So that's another scaling. Concentrated really on this narrow class of models, which are, essentially this attention kind of architecture, transformer architecture. Extremely impressive result. No reason to think that they're optimal. And 12 years ago, neural networks were nobody cared about neural networks, right? Who knows what happens in 12 years from now, right? Why should we think that we know that this is the best possible thing? Finally, I think it's prudent to invest at least a fraction of resources in alternatives. And, I'm not sure if I'm quite addressing the right audience with this point, but maybe. It's okay. Finally, okay, picture. So this is a picture downstairs here, and I think this represents GPT-4 at work. You can see there are like zeros and ones there, and this is kind of what machine learning is. But what we maybe would like to have is something like this, right? Which somehow complicated machine, but we sort of understand what the principles are of that thing. It's a little harder to know with that thing. Okay, I'll stop here. Thank you.
So related to your concluding thoughts, the main conclusion that I take from this, but tell me if it's wrong, is that the deep networks aren't doing that much.
I mean, the results are very impressive, so I cannot argue with the results, right?
But you can get them in a much simpler way.
Well, it remains to be seen. I'm very hopeful that we can, but we have to prove it, right? It's the ball is in our
On the data sets that you see.
Oh yeah, on this ones, yes. On that one, I'm 100% sure. Well, not 100, but 99.9.
Yeah, I mean, when it comes to transformers and attention, there's probably other things involved there. But like, your vanilla multi-layer perceptron.
Vanilla multi-layer perception, I'm completely sure that we can, just replace it with this thing. At least on smaller data when scaling is not a big issue. It's actually fast on small data.
So hyperparameters here are learning rate and some regularization, right? And do you see any sensitivity to that and how that compares relative to neural nets?
For us, hyperparameters, I forgot to talk about, well, no, I didn't forget really, but I didn't have time. So for our methods, everything is chosen automatically. It's actually AutoML. Because this is solving a linear system, and we know a lot about like parameters. We choose mini batch. So when you have a GPU, the EigenPro actually adapts to the GPU size and chooses optimal batch size, optimal preconditioner. So it's all very streamlined. There is not much choice in these parameters.
So for the recursive feature machines, right, it's equivalent to basically choosing, in some sense, a good norm, a good inner product. And then there have been like papers about how to do this, but it seems they have missed something. So do you have any comments about why
it didn't work?
Why it didn't work 20 years ago?
When I was a graduate student, there was one professor who liked to say, I'll see it when I believe it. I think we were just discussing with Miriam. It looks like it's very hard. If you don't know what you're going for, it's actually much harder to find it. Like neural network actually give us confidence that this is possible. Once you have confidence, somehow things work. But I agree, it's not that different from this. Like kernel alignment, metric learning, there were like a bunch of things of similar flavor. Even this EGOP itself, like if you look at this Annals of Statistics paper from like 2001, they also had some sort of similar thing. They proved that you can, they had some multi-index model and they proved that you can recover it. But I guess they just cared about some sort of rate, right, some optimal rate or something. So I'm not sure, it's not completely clear. I think it's just a matter of belief to a large degree. Faith, blind faith.
I think this kind of aligns. There's like, I see a broader trend right now in statistics with like people looking at double dipping, and it seems like generally if you try to do model selection and prediction at the same time, it's better to actually split them up separately.
Yeah, it's not exactly the same. It may be related, right? Because you are doing, well, we're not split, right? So, okay, neural network does it within the same optimization process. We somehow separate the optimization process. We don't separate the data, however. So it's not quite the same, but maybe it's of the same nature of things, I don't know.
Yes, in terms of the second part for the scaling, I was wondering if it is possible to make your algorithm like a recursive feature machine into like an online method so that you don't need to be worried about to chain this machine on a bunch of data at the same time, but you can have some streaming data and then you can keep chaining it. And then under this scenario, with your like the kernel machine would be has the same performance as just as chaining on large data at once.
It's probably possible. I mean, to some degree, that's what kind of neural networks does, right? It kind of chains them, and it's like it gets some data and it updates the weights and updates the predictors. I think you can do it probably more directly with the kernel. We haven't really thought about it. Maybe interesting too. There may be some advantages to do it in some sort of streaming. The problem is if you just do, well, okay, we're using stochastic gradient descent for the kernel machines, which is essentially a streaming algorithm in any case. So yeah, I don't see why we couldn't update. So right now we have a pipeline which is, okay, run eigenpro, then construct that matrix M, then rerun eigenpro, and so on. But you can probably put them together and do it much more efficiently, I suspect. Actually, I suspect that we can, when we do feature learning, we probably don't need to even compute gradients on the full data set. I suspect that a subset. But this needs to be explored carefully.
Any other questions? Okay, if not, let's thank Misha again.